We're looking at question 10 on the rate of reaction worksheet. This is taken from the DBE May-June exam from 2019. It's the rate of reaction question. So, they tell us, learners use the reaction of sodium thiosulfate, which is this little compound over here, with dilute hydrochloric acid to investigate several factors that affect the rate of a chemical reaction. Now, they're nice to us. They give us the balanced equation for the reaction. So the sodium thiosulfate plus hydrochloric acid gives us sodium chloride, SO2, sulfur as a precipitate, and H2O liquid. First thing they ask you to do is to define reaction rate. General definition. Okay, so we're going to define reaction rate, and it's the change in concentration, right, of reactants or products per unit, spell unit properly, it's very important, per unit time. Don't forget per unit time, okay, because it's a rate. Then they say, now this looks a lot more complicated than it actually is, okay? We just take one part at a time. 3 investigations, 1, 2, and 3, and there we go, there's our 3 investigations, are carried out. Here's the first one. The results obtained in investigation 1 are shown in the graph below. So we look at the graph and we go, here's my reaction rate in moles per second, fine. And this is concentration, which means they've looked at how concentration changes the rate of the reaction. And the first thing they ask is this. What is the dependent variable? Well, the dependent variable always goes on the x-axis. So that means for 10.2.1, my dependent is rate of reaction. So that looked a lot more complicated than it was. A lot more complicated. It's not what, so we didn't need to freak out too much. Then they say what conclusion can be drawn. So now we look at this, and again, I know it's a straight line. You cannot tell me, though, that they are directly proportional. This graph, if I extend, it will not go through 0. For it to be directly proportional, we have to have it go through the origin. What we can say, though, okay, and this is a much better way to say it, is that reaction rate increases with an increase in concentration. So as the concentration increases, the reaction rate increases, but we cannot say they are directly proportional. That looked, well, that's investigation 1, done. Investigation 2. The Maxwell-Boltzmann distribution curves A and B below represent the number of particles against kinetic energy for the reaction at 2 different temperatures. First of all, you need to recognize from this graph this one, because it's flatter and the average kinetic energy is higher. This is the higher temperature. Okay? Then they say this shaded in area represents the particles that can undergo effective collisions. In other words, they have more than sufficient energy. They are above the activation energy. Then they say to which line, what does line P represent? Well, that represents the activation energy. Okay. 10.3.2. Which curve A or B was obtained at the higher temperature? B, we just did that. 10.3.3. Explain in terms of collision theory, and I know you can't see what I just did. Collision theory, how an increase in temperature influences the rate of reaction. Well, this is a set thing. So, when we increase the temperature, an increase in temperature, right, means that we increase the number of particles. We increase the kinetic energy of the particles. Let's get this right. Right? Therefore, more particles have sufficient energy thus a greater number of effective collisions per unit time, and the reaction rate increases. And I'm not sure you can read anything I just wrote. Just go with it. Great. Last question. The potential energy diagrams X and Y represent the reaction under two conditions. Give a reason why curve Y differs from curve X. Well, this is the curve we get when there's a catalyst. Okay, so for 10.4, curve Y was obtained when a catalyst is used. Okay? Was obtained when a catalyst is used. Great. Now we get to the fun question. In one of the investigations, now this has got nothing to do with the curve. This is actually a normal stoichiometric calculation. In one of the investigations, 100 centimeters cubed of 0.2 moles of HCl per decimeter cube of HCl reacts with excess Na2S2O3. The solution is then filtered. After filtration, the solution 0.18 grams of sulfur is obtained. Calculate the percentage yield. So we have to remember percentage yield means this is my actual yield. I need to calculate theoretical yield. So let's do this one step at a time. First thing we need is from the chemical reaction, we need the ratio of the hydrochloric acid to the sodium thiosulfate. Okay, so this is 10.5. The original reaction they gave you was Na2S2O3, 2HCl, I don't need to worry about the phases, 2NaCl plus SO2, and this just goes on forever, S and H2O. In the question, they now say to me that I have 100 centimeters cubed, and I have 0.2 moles per decimeter cubed, and my actual yield of the SO2 was the sulfur, there we go, was 0.18 grams. When we do this question, I'm going to ignore this value until the end. Step 1, balanced equation. Got it. Step 2, I know the mole ratio. Brilliant. Step 3, calculate the number of moles of the thing I have, which is the hydrochloric acid. Now, number of moles is concentration times volume. Concentration, 0.2. Volume must be in decimeters cubed. So I'm going to take the 100, divide by 1,000. So that's 0.1. So this is the number of moles of HCl. I've now got to take that. Using the mole ratio, I need to know the number of moles of sulfur. So the number of moles of sulfur is 0.02 times, sulfur is what I want, HCl is what I've got, so it times by 1/2. That's how much sulfur I'm going to have created. Next step, I need to know what mass of sulfur theoretically I should have got. So 0.01 times 32. So theoretically, I should have got 0.32 grams. I didn't. I only got 0.18. So if I got 100% yield, I would have 0.32 grams. I only have 0.18. Therefore, so now let's do this one. There we go. So, my percentage yield is my mass produced, so that's what I actually got, over the mass theoretically that I should have got, times by 100. So 0.18 divided by 0.32 times by 100, and that gives me 56.25%. It's not a very high yield, but it is what it is. We're not asked to comment on it. We can't make any comments as to whether this is a good or bad thing in real terms, but we get 56.25%.